All right, y'all. So I promised you guys I would uh, solve one of these problems for you where we've been given all the features of a rational function and then we are trying to derive the equation of it. So when I'm doing this, I'm going to be switching back and forth between this screen and my whiteboard right here. So let's go ahead and copy paste the features from the problem onto my whiteboard so that I can just have those there. So first of all, let's talk about the structure of rational functions. Remember guys, rational functions are functions which can be written as a fraction of polynomials. So I know that this function should have some polynomial up at the top in the numerator and some other polynomial in the denominator. In general, we knew these features of rational functions had to do with different pieces of the fraction itself. The x-intercepts we had identified before as the zeros of the numerator. That is saying that we said the x-intercepts were. So I'm going to go ahead and put that next to the x-intercepts here. We said that the y-intercept was equal to r of 0. So it's the function with 0 plugged in for x. Asymptotes, we said, came from the zeros of the denominator. And wholes, if you guys remember, came from a removable discontinuity. What that meant was a common factor in the numerator and denominator. So in the top and the bottom, there should be some factor that is shared to make a whole. And then finally, end behavior was the quotient, right? The division of the leading terms in the numerator and denominator. So essentially, if I take the leading terms of my numerator and my denominator and divide them, it should be equivalent to the end behavior. So it seems like people were doing great with it, or well, so far so good for the most part, going from the equation to getting these features. But then once we went backwards and we were saying, oh, well, what if I knew the features and I wanted to solve for the equation, people started having some issues. So the thing that I think will be the most useful for us is to talk about when I know a 0, right? When I know a 0, how do I know the factor? How do I go from the 0 to the factor? The idea is if I know that, for example, let's use -5 because I think that one's going to be easiest to start with. If I know that x equals -5 is my 0, then the factor should be this an equivalent expression, but equal to 0. So if I add 5 over to the left-hand side, I would get x plus 5. And so I know that x plus 5 is my factor, because if you think about it, when does x plus 5 equal 0? When x equals -5. We said that the x-intercepts were the zeros of the numerator. So this factor of x plus 5 should be in the numerator. All right, so then what does that make the factor for 3/2? This is a little bit weird, but essentially, if x equals 3/2, then x minus 3/2 would equal 0. Now, I don't know about you guys, but having fractions is kind of annoying. Fractions kind of suck. So what I'm going to do is, in order to get rid of the fraction here, I'm going to multiply the entire equation by 2. The reason why I'm doing that is because then I would get 2x minus 3, right? When I distribute the 2, I get 2x minus 2 times 3/2 would be 3, and that equals 0. So my factor is 2x minus 3. So, and you'll notice this in general. It's actually very similar to why when we did rational zeros theorem. Why is it that I had, why is it that for rational zeros theorem, I had to take like the factors of 5 over the factors of 2? Why did I do that? Because there was a coefficient in front of my x cubed. Similarly, if my 0 has a fraction, then that denominator will commonly be related to the coefficient on my x term, right? That over 2 directly created the 2x, right? So, in fact, actually, I could have, for this, made my factor x minus 3 halves, but I'm not going to do that. I'm going to make it 2x minus 3 up top. Okay? So that's how you use it. So essentially, the x-intercepts just will give you the factors in the top. Similarly, because the asymptote is the 0 is the denominator, that'll give me the factor on the bottom. So if the 0 is x equals 4, then the factor would be x minus 4 equals 0. So I should have an x minus 4 on the bottom, right? All right, cool. So we've created most of our thing. I'm going to move these guys on down just for the sake of space. All right. Now let's look at this whole. So you guys will notice the order I'm going. I first looked at the x-intercepts to give me the numerator. Then I looked at the asymptotes to give me the denominator. Now I'm going to look at the whole to give me the last pieces. Okay, because if you remember, a whole will give me a factor in the numerator and the denominator. If the whole is at -2, then that would be like this guy here, x equals -2. How do I get it equals 0? I add 2 to both sides, so I get x plus 2 equals 0. So the factor is x plus 2. We said if it's a whole, then it should be on the numerator and the denominator. So I would have an x plus 2 up top and an x plus 2 down below, creating that removable discontinuity. The last thing that I'm going to do is I can actually look at my end behavior or my y-intercept. I could do either one of these next. The reasoning being that if I change this equation to allow it to have that end behavior of 8x, then it will also have the y-intercept of 15. And similarly, if I do something to this equation to give it that y-intercept of 15, it'll have the end behavior of 8x. They're just so they're reliant upon essentially the same thing, and what that is going to be some coefficient in front. Essentially, it's just going to be some coefficient in front multiplying. Now let's say that I don't have a coefficient there, like this function that I've created so far. Let's look at what the end behavior of this function would be. If you guys remember, end behavior can be found by dividing the leading terms. If I'm in factored form, I could find the leading terms by multiplying the x terms together. X times 2x times x would be 2x cubed. And down here, x times x is x squared. So the end behavior of this function currently, is currently 2x cubed up top over x squared on bottom. If I do that division, I get 2x. Now, 2x is not the end behavior I wanted, is it? I wanted an end behavior of 8x. So what do I need to do to turn 2x? What do I need to do to 2x in order to make it 8x? I need to multiply it by 4, right? So what I'm going to do is I'm going to take my function and I will multiply by 4. So I'm just going to have a 4 right there. And that will actually fix everything exactly how I need it. Because check it out. What is my new end behavior? Well, the leading term of the top would be 4 times x times 2x times x, which would make 8x cubed. The bottom would still be x squared. What's 8x cubed divided x squared? It is 8x. And then just to verify, let's check. Is the y-intercept of this 15? Well, when I plug 0 in, what do I get? R of 0 equals 4 times 0 plus 5 is 5. 0 times 2 minus 3 is negative 3. And 0 plus 2 is 2. Down below, I would have 0 minus 4 is negative 4. And 0 plus 2 is 2. All right, let's do this division out here. 2 divide 2 cancels. 4 divide 4 will cancel, but I'll still have the negative. But these negatives would cancel each other out, wouldn't they? So I'd be left with 5 times 3, that's 15. Oh look, it's the y-intercept. So this right here should be my function. Now let's go ahead and go back to the problem from my Desmos activity and check it on out. So I'm going to graph that. So the graph was 4 times x plus 5, x plus 5 times 2x minus 3, was it? Yes, and then times x plus 2. And on the bottom we had x minus 4 times x plus 2. Now, let's check it out. If we look at this function here, let's see what we got. We have a y-intercept of 15. We have an x-intercept of 1.5, which is 3 halves, and negative 5. 3 halves, negative 5 for the x-intercepts, y-intercept of 15. Excellent. So far, so good. What else did we need? We needed an asymptote at 4, at x equals 4. Well, here's x equals 4, and check it out. This function does have an asymptote right there. You can see the here, let me change the color on this guy. So you can see right here, let me go into projector mode as well. So do you see how this function, it's going down towards negative infinity at x equals 4, and over on the right hand side it's going up towards infinity at x equals 4. And then finally, looking at end behavior, it was supposed to have an end behavior of 8x. Let's look at where's y equals 8x? Does this follow that end behavior? Maybe I need to make my y-axis a little bit more differently scaled. Do you guys see how it's following the behavior of 8x, right, on its ends? Cool. So it looks like we have the function that we needed. So to summarize things, y'all, essentially, the only thing that's really that crazy new is this idea of going from the zeros to the factors. And the really weird one is when it's a fraction. If I knew that my 0, for example, let's say I knew that I had an x-intercept at, an x-intercept at 5 over 3, then I would know that x equals 5/3. In order to get that equal to 0, I would subtract 5/3 over, so x minus 5/3 equals 0. And if I wanted to get rid of the fraction, I would multiply everything by 3, so I would get 3x minus 5 equals 0. A factor of 3x minus 5 is going to give me that x-intercept of 5/3. Cool. If you guys have any other questions about these types of topics, go ahead and ask me in our class Discord, please. All right, have a good day, y'all.